Hello, this is our first in a series of lessons on scientific computing. We're going to start with ordinary differential equations. And the first approach that we're going to use for ordinary differential equations is also the simplest. It's called Euler's Method. So we're going to use two different strategies for employing Euler's Method. And why are we interested in Euler's Method? Well, first of all, it's an algorithm for estimating solutions to first-order differential equations, and it turns out that often in nature, the laws that we discover that nature obeys are solutions, or described as first-order differential equations, and so that's one of the reasons it's interesting. And of all the methods we're going to cook up this semester, Euler's method is the most straightforward, so that's why we're doing Euler's method. How does it work? So the idea is you have this thing, we're going to call it the state. Now it's simply a collection of variables that you need to specify whatever the system is doing at any given moment in time. So it could be a single variable or it could be multiple variables depending on the complexity and the number of particles and so on in the system. But the point is there's some rule, usually derived from some law of nature like Newton's second law or something like that, that tells you how the state is going to vary in time. And it's written this way: the rate of change of the state is equal to some function of the state now and the time. Now, state S could be more than one thing. It could be positions and velocities, or it could be temperatures, or who knows what it could be, some set of those. The idea of Euler's method is to allow time to progress just for a brief period of time, and that allows the state to change just a little bit. And we can approximate the derivative of the state as the finite change in the state divided by the finite change in time. And all we're going to do is to multiply both sides of that expression by delta t, and you get an expression for the change in the state. That's the whole thing right there, that the change in the state over some short period of time is approximately equal to this function, which gives us the rate of change of the state, times the corresponding change in time. And now all we have to do is to add the change in the state to the old state to get the new state. So these two expressions, that the change in the state is the function times the change in time, and that the new state is the old state plus the change in the state, those give us Euler's method. And you can see graphically the idea is I've got the state as a function of time. I want to know what's the change in the state. Notice that if the time is finite, that the change in the state won't exactly be the solution, but it'll be very close as long as the change in time is very small. That's the idea. So let's take an example. Let's say we're going to study radioactive decay. We'll let the state be the number of parent nuclei that remain at any given time. The rule for radioactive decay is that the rate of change of the state is equal to minus a constant times the state. In other words, the rate of change of the number of nuclei in the system is minus a constant times the number of nuclei there right now. Let's say we start with 100 nuclei and we have a lambda of 0.01. That means that you're going to get one decay per 100 seconds of source nuclei. So if you have 100 nuclei to begin with, then you'll get about 1 a second. If you wait for 10 seconds, you're going to lose about 10, and then there'll be 90 left over. That's kind of the crude idea. So let's see how that works. How do we compute this kind of thing on a computer? So the easiest way to do it is to use a spreadsheet. And the plan is to connect together cells in the spreadsheet in order to achieve some computation. So the way it works is you'll notice that you can type into cells formulae. Anyway, you can put in a different formula into each cell that computes a number that depends on the contents of other cells. And I just want to point out a couple of things here. The most important idea is that there are different kinds of references. So if you notice in cell F3, for example, the formula there is $B$2 plus $C$2 plus $D3 plus E3. And those dollar signs tell you how the formula copies from one cell to the other. If you put a dollar sign in front of an address, it means you're going to keep that thing pinned to that value. So $B$2 is a reference to column B, row 2. But if you copy that cell to a new cell, the B is a relative reference, but the 2 is absolute. That means the 2 is going to stay put at 2. But if you copy that formula down or copy it over, you're going to get a relative reference, which means, for example, in cell F3, B means go over go over 4 cells to the left. If you copy that over to G, notice that in G2 there is a $C$2. So when that formula got copied to G2, the B changed to a C, and it still means 4 cells to the left. In H2, if you go down, you'll notice that C changed to a D. It still means 4 cells to the left. But notice when you copy the thing down, H4, if you look at H4, it's still $D$2. So the $2 stayed pegged the whole time. On the other hand, the $C$2 stayed pegged to that particular cell because we pegged the C and we pegged the 2. Similarly, you'll notice the $D$3 in cell F3. If you copied that down to F4, it changed to $D$4, and so on. So the D stayed pegged, but the 4 was allowed to remain a relative reference. And finally, the last thing in the sum, E3, E4, and so on, those are both relative. So that means 1 to the left, and then in the same row, and so on. So by putting dollar signs in front of address components, you can peg those to a particular cell. We'll see in a moment why that's important. Okay, so we're trying to solve the decay problem, and notice what I like to do in my spreadsheets is put the constants up at the top for any given problem, and then the stuff that depends on time, that goes into rows in the table below. Notice also that we have labels for these rows, so time, S, and delta S, those are going to depend on time, and so those labels will help us later when we go to make graphs. Now S is going to start at 100, T is going to start at 0, and notice delta S is given by a formula, and let's look at that formula. It's $C$3, $C$4 times C7. Notice that that's lambda times delta T times S. That is the differential equation. That is the f of S and T. And so delta S is determined by that rule. T is going to be the last T plus delta T. Delta T is a cell in my constant row. And then S is going to be the last S plus delta S. And of course delta S is always going to be computed by the rule. So now we can compute all the remaining rows at later times by simply dragging these formula down. And you'll notice that in the first second we lost about 1. But now in the second we lost a little bit less than 1 because of the fact that the number has dropped down to 98 now, and so on. So you can see that this is an approximate scheme whereby we compute the expected number at some later time. Of course, in a real nuclear decay, you can't lose a fraction of 1. You can only lose 1 or not 1. But this is a continuous sort of model of radioactive decay that tells us, on the average, what we'd get if we had many, many different samples, all of which started with 100. On the average, we'd have 98 left after 2, and 97.03 left after 3, and so on. Okay. I also just wanted to point out that there are many different spreadsheets on different platforms, and they all work the same way. Here's OpenOffice. I just showed you numbers. Here's Excel. It all works basically the same way. You can do this also on Windows, and you can do it on Linux if you want to. So, how do you make a graph? Well, the idea of to make a graph is you simply drag the calculation down to get more rows, and then copy those formula down, and you can see that that lets the calculation continue for greater and greater values of t. And then you select the rows you want to graph, and then once you get the correct rows selected that you want to graph, you simply include a chart. So you pop a new chart in and choose scatter plot. So that's how you make a graph of data. You'll be doing that for your first couple of projects, as we use spreadsheets to do those. But and this is a little bit of an older version of Excel I used to make this, but it works more or less the same way with all different spreadsheets, all different versions. Okay. Now, so that's how you do Euler's method with a spreadsheet. The other strategy we're going to be using is procedural programming. We're going to write computer programs that do the same basic process, except in this case there are no cells, there are variables. So here's a simple Python program. You define lambda dt, the initial value of s, and the initial value of t, and then you write a loop. This is a loop that lets I go from 0 to 99. The range command returns a list of values, and the way a for loop works is you say for I in list, and I will take on every value in the list as it goes through all the iterations. In each iteration, we're going to print out the current value of t, the current value of s. Now the next step is s plus equals minus lambda times s times dt. That's the differential equation. That's Euler's method right there. Notice that s is getting incremented by an amount that's equal to delta s. So this increments s by an amount of delta s, and then t gets incremented by an amount dt, and then the loop repeats. If you actually run this thing, you get the following result. Time goes from 0 to however far, I guess it goes up to 99 in this case. And s starts at 100, and then it drops. Notice it's dropping exactly the same way it did in the spreadsheet, except now it's just printing out the values, and it's a procedural loop instead of a spreadsheet. Now the problem is, how are you going to visualize that? You need some kind of a graphing package. The good news is that Python has a bunch of libraries out there that folks have cooked up to do graphs, and the one we're going to use first is called PyLab. It's sort of a clone of the commercial product called MATLAB that has similar features, and you can find it on the web at matplotlib.sf.net. So go and grab yourself a copy. All we have to do to add a plot to our program is import the PyLab module at the beginning. We have to collect a list of values. So we're going to collect a list of times and collect a list of s values. And then at the end, we're going to plot the time and the s list and show the resulting plot. Here's the code that actually does it. You'll notice in the loop we're also adding the time and s to these lists using the append method of the list to collect those values of s and t. But that's basically it. It's the same program. It works the same way. It's just that now we're going to plot the results. If you run the program, you get this. Notice it's a nice little graph of the s value versus time, and we can improve upon it a little bit by adding another list, the exact solution list, and we put in an analytical expression, which is the exact solution for this differential equation, which you guys all know how to find. And then at the bottom, when we plot the time, the solution list, and we're going to make that green dots. Then the time and the exact list, we're going to make that a red line. And if I graph this graph, you'll notice that the green dots are my Euler's method solution. The red line is the exact solution. And that's the way it works.